Wrong, 1 second.
Start again, sorry.
All right, good morning once again, everybody. We are Design Team 9. We were working on a robotic transportation vehicle prototype for Texas Instruments. Today we'll be talking about wireless RF communication. Let me introduce my team members. This is Stevie Baldwin, our document prep, Grace Jones, our lab coordinator, Alex Koshman, our team manager, and Hao Tiantai, our webmaster. And I am Timur Yaprek, our presentation prep. Let me quickly go over the agenda this morning. Grace will be giving an introduction as well as specifically the electromagnetic spectrum and some FCC regulations, as well as some simple RF systems. I will then be talking about wireless communication systems, modulation, demodulation, methods of communication, as well as some ways of extending range of an RF system. Alex will then be talking about noise and how it affects wireless communication systems. Hao Tian will then be talking about how we're going to be going about powering our USB receiver, as well as other electrical components within our vehicle. And Stevie, last but not least, will be giving a demonstration. So with that, I'll pass it on over to Grace.
Hello, as you said, I'm Grace Jones. I'm the lab coordinator for Design Team 9. I'll be giving a brief introduction into RF systems. I'll be talking about the electromagnetic spectrum, radio spectrum in particular, FCC spectrum, allocation, and RF system structure. So here's the electromagnetic spectrum. It spans sound all the way to cosmic rays. It spans sound to all the way to cosmic rays. And we will be focusing on the radio spectrum, which is the 10 kilohertz and 10 gigahertz range. So the radio spectrum. As I said, this is the radio spectrum, and this is where the RF communication is done over radio frequency, from 10 kilohertz to 10 gigahertz range. More specifically, we will be operating in the ultra high frequency range, and even more specifically on the ISM band, which is a band allocated by the FCC for industrial and scientific and medical usage. The ISM band, these are center frequencies here actually listed, but the 315 to 915 megahertz range. And also, I'll be talking about different types of RF communication, like cell phones and Wi-Fi, stuff like that. Those operate at higher frequencies in the super high frequency range, 2.4 gigahertz of the ISM band as well. Frequency allocation. So the FCC has broken up the radio spectrum to have a more organized communication system and to have less interference from other sorts of things. So recently, in like 2009, from the conversion from analog to digital television, it freed up a portion of the radio spectrum that could be used for medical usage, specifically because they had a lot of noise and interference in their systems. So they jumped on that as soon as the band was free. So they operate now in that range as well. And so the M band was an added portion to the ISM. In the US, we operate, as I said, around the 315 to 915 megahertz range, the US, and all these different countries have different frequencies that they operate in the RF bands. So yeah, these are all center frequencies here listed. And this is a breakdown of that too, even more specifically. It's all coded, the FCC. You can look this stuff up on fcc.gov. They're all coded, they're all sectioned off. It's very, very, very particular because you have some portions that are used for, not just for communication, and that are licensed. So if you operate at a licensed frequency, you have to make sure that you don't interfere with those licensed ones, because these are unlicensed frequencies that anyone can use in all these different countries. And wireless communication systems. There are different types of communication. We have simplex communication, half duplex communication, and full duplex communication systems. All these are RF. And the duplex just means bidirectional. So the half duplex and full duplex allow communication in both directions. Simplex only allows communication in one direction. And an example would be radio or television, something like that, that you don't send a signal back to the transmitter. But it also comprises of a transmitter and a receiver. Half duplex allows communication in both directions, but not at the same time. So it'd be like a walkie-talkie or like something like that. You can think of all different types of usages and applications. And then full duplex RF systems, which would be like cell phones. They will allow communication in both directions, so it receives and it transmits, and it can do it at the same time. So cell phones and like Wi-Fi, stuff like that, will operate and they would be classified as a duplex, full duplex system. This is the basic structure of an RF system. It composes of a transmitter and a receiver and some sort of communication channel, which is just a medium, air in this case. Air has noise associated with it, white noise, and Alex will be talking about that even more specifically. But the transmitter composes basically of a low frequency signal that you're going to send, a modulator which modulates and encodes the signal, maybe phase, amplitude, or frequency, and then an amplifier which amplifies the signal to be sent to the receiver. And the receiver is comprised of an amplifier to amplify the signal that it was received, a demodulator, and some sort of output so that you can see the signal or receive the signal and take it and put it somewhere. They also have, it's not actually in this diagram, they also have a tuner, and a tuner is just like a resonator LC circuit that amplifies oscillations at certain frequencies and reduces oscillations at other frequencies. So furthermore, isolate the signal to reduce all sorts of noise that you would get and extraneous signals from other transmitters or anything in the same frequency range that's operating near your transmitter receiver construction. With that being said, I hand it off to Timur, who will talk about modulation and demodulation.
Thanks, Grace. Once again, I'm Timur. I'm the presentation prep. Modulation is basically a process that varies a high frequency carrier signal in order to transmit information. As you can see here, there are three separate parameters of a cosine sine function that each have their own modulation technique, amplitude modulation, frequency modulation, as well as phase modulation. The main purpose of this is in order to translate the message signal into a desired range of frequency spectrum for signal processing purposes. And with that, amplitude modulation. AM, I'm sure you guys are all familiar with. It's one of the earliest radio modulation techniques. It's basically, as you can tell from the name, modifies the amplitude of the carrier signal before transmission of the message signal. The main purpose of this is so that it takes advantage of a certain demodulation technique called envelope detection. Frequency modulation. Frequency modulation, once again, you can tell from the name, it varies the carrier signal's instantaneous frequency. This actually requires more bandwidth, but has better noise immunity as compared with amplitude modulation. The amount of frequency deviation directly reflects the transmitter output frequency, and it is mainly used for radio and television broadcast purposes. Phase modulation is very similar to frequency modulation. Varies the instantaneous phase of the carrier signal. Basically, as you can see here, just lags the frequency modulated signal. The next one is digital modulation. Here are some digital modulation techniques: amplitude shift keying, frequency shift keying, and phase shift keying. They correspond to their analog modulation techniques. Have the same or similar properties as the analog modulation techniques do. Keying just refers to of the on-off variety, meaning that it has a binary modulation technique to it. Demodulation. Demodulation takes in the modulated signal, basically amplifies the signal, and then filters the signal in order to retrieve the transmitted information. Let's see. Yeah, depending on how the signal is transmitted or modulated, the receiver will use a corresponding demodulator. These are some ways of extending the range of an RF system. You can either increase the output power of the transmitter, increase the sensitivity of the receiver. You can do both, or you could use high gain antennas. And with that, I'll pass it on over to Alex, who will talk a little bit about noise and how that affects wireless communication systems.
Alright, again, my name is Alex Koshman, and I will be going over the noise in a system. Noise can be a big problem. It can cause inaccuracies in the signal. It drastically reduces the quality and also can cause a lot of power loss. So we will spend lots of time trying to reduce the noise in the system to prevent those negative effects. This is an example of white noise. It's just a random function that it can be found over the air. Some other causes might be another transmitter in the area that might be transmitting some similar frequency that can cross with the input signal or the sending signal that we're putting out. Or also a malfunction could happen that can send some kind of other frequency that can cause more noise. So I'm going to be going over two kinds of noise, AM and FM. So the first one that affects AM the most is the white noise, which is the random signal. The blue line here is an example of an AM signal. However, white noise will cause small jumps in that line. So the solution to that is an envelope detector, as you can see the red line. That will reduce any of those little noise jumps. That will reduce its effect. However, it still causes a lot of power loss, and the quality still will drastically drop. Alright, so next up is FM noise. FM is much better against noise than AM, but it still has an effect. So this is an example of a carrier frequency. What it should look like is just straight up and down. However, with noise, the carrier frequency can leak in and out of that value that it's supposed to be. If any of you have taken ECE 457, we spend about half the class trying to figure out mathematically how to solve that. So the phase deviation function is actually how we solve that. White noise is a Gaussian function, so we can mathematically solve for that. And so from there, we can actually predict what the system is going to do based on the noise inputs that are random. So from there, I'll pass it on to Hao Tian, who's going to talk about how we're going to power our receiver.
Thanks, Alex. My name is Hao Tian. I'm the webmaster of Team 9. I'm going to talk about how to power our receiver. We are using a USB 2.5 receiver, so it needs power of 5 volt DC. This is a picture of the USB port. The pin number 1 is connected to the positive 5 volt, and pin number 4 is connected to the ground. But our motor is working at 24 volt DC, so we need to convert the 24 volt DC to 5 volt DC. So this is a picture of a DC to DC converter. This is called buck converter. So we use a switch to control this circuit. So when the switch is on, the current goes through the switch and then to the load. When the switch is off, the current goes through the dial and then to the load. So we use a dual cycle to control the switch, so that we can get a 5 volt output. So the dual cycle is 0.2083, so which we can get a 5 volt DC output. And I'm going to pass it to Steve to talk about demonstration.
How you doing? I'm Stevie Baldwin, and again, I'm the doc prep for Team 9. I'll be going over a brief demonstration. I'm going over a simple, well, not simple, but an RF communication system that's very known and used every day as Wi-Fi. We all know this we're using our cell phones, laptops, tablets. Let me run the program really quick. I'm just going to run a couple commands in the command window. How Wi-Fi works is it sends a signal from sends a signal through the internet, and as Grace mentioned earlier, the frequency for Wi-Fi is around 2.4 gigahertz. What it does is when you want to go to a certain website, you send the data, you send requests to the website, and then the website in returns receives that request and transmits the data back to your computer. Through this process, it may go through as many as 5 to 20 hours, depending on the fastest way that it takes to get back from the website to your computer. And just do a couple simple commands, you can actually track how long this takes and the process, the route that it takes to get from the site, the data to get transmitted from the site to your computer. Anyone who's taken EC442 will be familiar with the ping command and the tracer command. So for the first website I'm going to use, well, first when you type in ping, it comes up with several commands, or several options, I guess, depending on the applications or whatever you want to use for your particular, what you're interested in. And the first website I'm going to look at is the MSU website, which we all go to at least every day. I go to it every day. So I'm going to type in the ping command. I'm going to type in the -n, which is the number of packets I'm going to send. And for time constraints, I'm only going to send 5 packets. We put that, and then we put the website we want to go to. And again, it sends data from the website to this computer. And when it's done, it tells you, okay, the packet sent is 5 packets, the packet received, we actually lost a packet, 4 packets, we lost 1 packet. It gives you the minimum and maximum values and the average values. Again, this doesn't take that long, it takes 4 milliseconds, but since the actual MSU router is actually, on campus, it doesn't take that long to receive data from the router. But if you try something a little further, like let's want to go to the University of Florida's website. And then again, we sent 5 packets, we received 5 packets, we didn't lose any. And the average time is about 46 milliseconds, which makes sense because we're not in Florida, so it takes a little bit of time to get from the router from Florida to the actual MSU router where we receive the data. And let's try something again a little further. The University of Tokyo. And as you can see, this takes significantly longer. Well, again, we sent 5 packets, we received 5 packets. We took an average of 239 milliseconds, which seems long compared to the other ones, but the fact that you're receiving data from across the world, 239 milliseconds doesn't seem that bad if you think about it. As far as where this data is going, as far as the different routers it's going through, like I said, being received and transmitted, as Grace and Timur talked about, the different methods for that. We can use the tracer command to figure out where actually the path is taken to get back to our website, to our computer, or from the website to our computer. So I'm going to start with the MSU website that we went to the first time. And again, it tells you how many routers it goes through, the time it takes, and then the domain name for each router is specified just through whoever owns the router has a certain name that they give to their router. And let's try University of Tokyo's website, or University of Florida, I'm sorry, University of Florida's website. So you see where that path takes us. Goes through quite a bit more routers, it's going to take longer to get from there to here. And again, these star commands, or these stars that pop up, it's an actual router, but the fact that whoever owns the router doesn't want their name being displayed, like it does. Usually when it has stars, it's just blanked out. This one might do it actually. Where whoever owns the router doesn't want their name being displayed for whatever reason, the name of the router. So the 15 is the actual router, but for whatever reason, the name's not been displayed. But again, this takes about 16 routers for it to receive, where it's transmitted and received from each of those routers till it gets to the computer, I'm sorry. And that is the end of the demonstration. In conclusion, Timur went over the introduction, and Grace went over the electromagnetic spectrum and RF systems. Alex then went over the noise, and then again, Timur again went over the modulation and demodulation, and Hao Tian went over the power and how we're going to power our USB device, and I did the demonstration. Are there any questions?
Since I'm here, let me ask you a question. So you said those were going through routers. Weren't they really just going through servers, not routers?
Well, yeah, servers, and then the servers will then send it or transmit it to a router.
Well, you think of a router as something that, I guess you could There's more servers. I think of a router as the wireless device. That,
Right.
yeah. Okay.
Yes.
So when you did that last trace, one of them said Internet 2, I noticed. Is the number of steps going to be less if you're going university to university compared to,
depends,
say,
like
if
I
you were
said,
going to some random website in Florida?
It depends. The internet, like I said, it's a very complicated algorithm that tracks the fastest path that it takes to get from the data from the website to your computer. So it's changed depending on, I guess, different bandwidth being used at a certain time. They're not going to send it through that router, obviously. They'll send it to a different path.
All right.
Yeah.
Just curious, what happens to the data packet when it's lost?
Well, yeah, in 442, took the class, there's certain, I guess, protocol that it will take where there like, there'll be a certain time slot where you can send messages, and then if it's lost, then it will, the router will pick up, it's a certain sequence, like 1, 2, 3, 4, 5 that it sends to make sure it gets all the data. And if it goes from, let's say, like 2 to maybe 4, then it'll know it would know that it lost 3, so then it will send a request back to the receiver saying we didn't get 3, and it'll send that back, and then accordingly adjust the data. Any more questions?
Good job.
Thank you.